Let us hear a sound. This is the sound of 440 Hz. In time domain, this is what the sound wave looks like. A sinusoidal wave of frequency 440 Hz. Let us hear one more sound. This is the sound of 250 Hz. It sounds very different but has almost the same characteristics except the frequency. Things get complicated when we hear both these sounds together. It might sound similar to the previous ones, but if you are given a task of reproducing this sound, it would be almost impossible to do by just looking at the time domain waveform. But if we find out what frequencies are contained in this sound wave, then we can surely reproduce it. This is where the Fourier transform comes to our help. It converts the time domain signal f of t into frequency domain f of omega. Remember that it is the same signal just written in a different form, hence the name transform. We will not derive this formula here, but try to get an intuitive understanding of it. If I asked you how many $5 bills would make $15, you would divide the total 15 by 5 and get the answer as 3. Similarly, we can ask the question, how much 250 Hz sinusoidal component is contained in the signal f of t? In this case, we can do something similar. Divide f of t by e power j 2 pi 250t. Here, we have expressed the sinusoidal 250 Hz component using the Euler's formula. We can rewrite it as f of t into e power minus j 2 pi 250t. Now we can integrate this across the time to find the contribution of 250 Hz in the entire signal f of t. In general, for a frequency omega, we can write it as this equation. This gives us the Fourier transform. Thanks to Brian Douglas for this simple explanation. Link to his video is in the description. Remember that this is not the derivation of the formula, but just a method to understand it better. There is also another beautiful way to understand Fourier transform. 3 Blue 1 Brown does a fantastic job in his video explaining it graphically. I just loved it and you should definitely check it out. Link is in the description. Let's look at the Fourier transform of some commonly used signals. This is the Fourier transform of cos of omega naught t. This is the direct delta function and it is 0 everywhere except at omega naught. Thus we can show the Fourier transform of a cosine signal as two impulses in the frequency domain. Negative frequencies are only used for mathematical convenience and they do not have any physical meaning. Let us see one more example. Consider a rectangular pulse. The Fourier transform of this signal is a sinc function. What it shows is that this signal contains all the frequencies in the spectrum. And it makes sense. Every frequency component can only rise as fast as its frequency can allow. But to get a steep rise, we can use infinite frequencies to create this rectangular pulse. Or in other words, what we are doing is breaking any signal as a sum of sinusoids. If you are wondering why are we expressing all signals as sinusoids, this is because sinusoids are extremely easy to deal with and they do not change their shape on passing it through a linear time invariant system. What it means is the frequency of the signal will remain the same no matter what linear operation you perform on it. But real life systems work in a different way. For example, take a spring with a mass attached. Stretch it and allow it to come to rest. The position of the mass is a sinusoidal wave but getting damped over time due to viscous friction of the surrounding air. Unfortunately, the Fourier transform does not include the damping factor. So let's add that damping factor sigma to our signal. Now, we can take the Fourier transform of this signal. We can rewrite it as e power minus sigma plus j omega into t. We can call this new variable sigma plus j omega as s, and this new equation in s is called the Laplace transform. In other words, now we are expressing any signal as a combination of sinusoids and exponentials. You should also observe that Fourier transform is a special case of Laplace transform when sigma is 0. Or in other words, Laplace transform is nothing but the Fourier transform for different values of sigma. But how do these transforms help us? Let us take a simple example of a RC circuit. I can write the output voltage as a differential equation like this. For non-electrical engineers, just treat this equation as some random differential equation that you need to solve. To solve this, one way is to use ordinary differential equation techniques, but that can get tricky and complex for higher order systems. Another way is to use Laplace transform. Now, to find the Laplace transform, we do not solve the integral but just look at the lookup table. For example, let us take the lookup table for Laplace transform for a differentiation which is highlighted in pink. Laplace of df by dt is equal to sf of s minus f of 0. It has converted a differential equation into a linear polynomial. In our case, the initial output voltage is 0, so we can take the Laplace transform of this differential equation and write it as this. We can find out the ratio of V out to V in, and this is also called the transfer function of the system. It tells us how the output will respond to different inputs. If you want to get the output in the time domain, you can take the inverse Laplace transform of this equation using lookup tables. Inverse Laplace transform will convert the S domain back into the time domain. But we do not want to solve this equation. We want to understand the frequency response of the system. What that means is, how does the system behave for different frequencies? Does it attenuate it, or does it amplify it, or does it create a delay for that frequency? For that, we will study what are poles and zeros. Poles are the values where the system blows up to infinity, and the zeros are the values where the transfer function goes to 0. In this case, we do not have any zeros, but we have a pole at s equal to minus 1 by cr. The way you find poles of a transfer function is by finding the roots of the polynomial in the denominator, because at those values, the value of the transfer function will go to infinity. Now, we create a 2D plane of sigma and j omega. This is also called the S-plane. We mark poles of a transfer function with an x. Let us say we had a 0 in our transfer function also. Then along with the pole, we have an additional 0 at s equal to 1 by omega naught. We would mark it with a circle on our plane. At this value, transfer function goes to 0. We can also have higher order transfer functions. Take the example of this RLC network. I am not deriving it, but we can arrive at the output to input transfer function as this expression. Now, this is a second order transfer function. The roots of this polynomial will be either real or imaginary. The imaginary roots will be conjugate as all the coefficients of this denominator polynomial are real. This will always be the case for any real system. The values of R, L and C cannot be imaginary. But how do we obtain useful information from these poles and zeros? This is where Bode plots will help us in the next video. Let us have a look at what we discussed today. We understood that Fourier transform is required to identify what frequencies are present in a signal. But Fourier transform does not include the damping factor, so we introduced the Laplace transform. For any system, we can express the output to input ratio in S domain, and this is called the transfer function. Then we can identify poles and zeros of this transfer function and plot it on an S plane. See you next time.